Hey, what's going on YouTube? If everything is hooked up correctly, I think that we should be live right now. This is exciting. This is the first real stream to this brand new channel. Welcome. My name is John. I am a former mathematician. I studied pure math in undergrad a while ago, and I decided not to study mathematics at a research level and become a professor and all that. Instead, I worked in Silicon Valley for the last 10 years, working as an iOS developer. But now I'm trying to rebuild my passion and love and hobby in mathematics, and I want to practice and just share my love for math with all of you. So this is a brand new channel. The concept is that it's going to be a practice stream. So I'm just going to be live practicing math. And part of that is going to be teaching. So I'll be teaching some concepts. Today, as the whiteboard shows, we'll be working on proofs by induction. And then, every day it's going to be a little bit of both. So we'll be doing some simple lectures. I'll be working through problems that I've previously solved, and then I'll be like live studying and like live working on brand new problems that I haven't seen before. So it's going to be a blend of both ideas. And I hope you enjoy it. It's going to be totally new. I don't know how well this is going to translate over. I used to do this, or I do this on another channel with classical guitar. We'll see if it translates correctly to math. We'll see. This is a brand new channel, so I doubt that we're going to get a lot of views during this, but we'll see, maybe. So since there's not a lot of people here yet, I'll just do at here practicing math. https youtube.com/jcpracticesmath/live. Cool. Okay, so let's get started. I've got a topic for today. Last time, I have one video on the channel, so let's just revisit. Last time, we worked on showing some number theory for kids. And so these were some simple math facts that I was showing without any kind of proof about some basic facts about numbers. So we're going to continue with that, and I'm going to have one new thing that I do show kids. And it's, I think, a really lovely place that will connect really well to proofs by induction. So let's get started. So I like to show this to a lot of people. I like to show math concepts that most people don't see in high school. Most people don't ever see unless you study math properly. I like to show this one. So there's a famous story. It's a very nice romantic story about a mathematician named Gauss. So this guy was one of the most, he was like a very famous number theorist, as well as other types of maths. Number theorist, he proved facts about prime numbers. And depending on the audience, I may just leave it at that. So right now, if I'm just explaining this to a kid, I'm probably just going to leave it there. They know what a prime number is. I don't need to get into like more gritty details about what that is. But he proved some facts, fascinating facts about prime numbers. We'll just leave it there for now. But there's a wonderful story that when he was a kid, the teacher would, whenever the class was acting up and whenever they were being rowdy and whatever, like as a punishment, the teacher would give them the challenge Okay, add all of the numbers. Add up every number up to 100. Go. And you just have to do it one by one. Like 1 plus 2 is 3. 3 plus 3 is 6. And then, plus 4 equals 10. And then 10 plus 5 is 15. Plus 6. My equals aren't quite accurate here, but you know what I mean. So we're adding all of the numbers, and if you do it again and again, it's a totally tedious chore. But Gauss was a freaking little genius, and he took a look at the problem, scribbled a little bit, and then said, what is it, 50-50? I believe it's 50-50. And then he went back to doodling or playing with his toys or whatever. But he was able to solve this problem really fast. And it turns out he found the story is that he found a great solution to this. So what we're going to do is, maybe we'll switch to another letter. We're going to call this number n. Okay? Then, well, you could also write n backwards. You can write it as 1 plus 2 plus ... plus 99 plus 100. Then, if you add those two together, I don't really like the separate color. Let's just keep this as white. 1 plus 100 is 101. 2 plus 99 is 101. And then each time, 3 plus, like just double checking ourselves, 3 plus 98, that's also going to be 101. So every single term, if you just keep adding in this way, every single term, 99 plus 2 is also 101. 100 plus 1 is 101. And then the right-hand side is 2 times the number that we're interested in. So, great. Now, how many terms are there? Well, there were originally 100, and so there's still 100 terms. So, this is 100 times 101 is 2n. Therefore, a fancy symbol for therefore is like 3 dots like that. N equals 100 times 101 divided by 2, which is 50 times 101, which is 50-50. So, just like what I said earlier, he found that answer, and he found that answer quickly on his own. So this is a really clever, fascinating, really nice, beautiful insight. And it's a really wonderful proof by insight, one might say. Like a clever argument and a clever proof for something like this. It's just like, it's a really lovely thing. And then, but this idea, these are called the triangle numbers. T of n is 1 plus ... plus n. So if you add up the first n terms, then, for example, t of 1 is just 1. The second triangle number is 1 plus 2, which is 3. The third triangle number is 1 plus 2 plus 3, which is 6, and on and on. We saw that the 100th triangle number is 50-50, etc. Well, it turns out that pretty much everything here can just be substituted right here. That can be an n. So this number 100, here, why don't we use a different color for purposes of highlighting. That 100 we can replace with an n. This 100 becomes an n. And then all of these become n plus 1. Because here, if that's n, that one's n plus 1. This is n minus 1 plus 2. So all of these terms are n times n plus 1. So right here, the formula is going to generalize as n times n plus 1 divided by 2. So this is a marvelous, nice, elegant little formula and solution. You can just plug in any number, like 50 or 100 or 1,000, and you can compute that sum instantly. Because it's just, instantly, it's a lot easier to multiply two numbers and divide by something, divide by 2, than it is to add 1,000 times. So that's way, way faster to find those numbers, which is cool. And Gauss was a little genius for it. So that's something I like to show kids. And it's a great story because you can be like, well, when he was your age, one of the first mathematical insights that he had is this famous formula. But now, today, we're going to be doing a little bit more practice for people who may or may not know the term induction. So let me explain the concept. Induction is one type of a proof strategy. So it's one kind of proof. The idea is that if you have a statement, a proposition, if P is a proposition, to prove P of n for all numbers what you can do is show, I'm going to simplify a little bit and say that you want to show the first example. First, you show that any one statement is true for one number n equals 1. This is called the base case. For example, typically n equals 1. And then, so first you show it's true for one number, and then you show that if it's true for one number, then it's also true for the next number. This is called the inductive step. So, I like to liken it similar to dominoes. Dominoes? I don't know if that's the if that's how do you spell it? Does dominoes have an E at the end? I don't know. Anyways, if you have an infinite number of dominoes, and each one, first, the base case is showing that you can tip over one. That if you can knock over one domino, like that the statement is true for one domino, you show that it's true for one number. And then, secondly, you show inductive step. Here, let's get a little bit of a clear presentation of that. Why don't we say, that the inductive step space is small. I don't know. What I'm trying to get at is, first you show that the statement is true for one domino, and then you show that all of the dominoes are close enough to one another that if one of them falls, that it will tip over the next one. So then you know that because the statement is true for one of them, and that all of the future dominoes are all within one space of the next, then each one is going to keep knocking over the future one. Knocking over the first, knocks over the second, knocks over the third, on, and then therefore the statement is going to be true for every number. So that's the goal. That's the strategy of induction. Let's see what it looks like in this example. So we've already shown a proof of the triangle numbers formula by this clever insight that Gauss had. Prove. I don't like the T of n notation. I think not a lot of people know that. I prefer to just be explicit that the sum of the first n numbers equals n times n plus 1 divided by 2 by induction. So this is a great canonical example of a proof by induction. So here's the proof. First, we show the base case is true. I'm going to be very explicit, just like writing out everything, but later on when you've practiced a lot more proofs, you'll kind of omit some of the details. So when n equals 1, the left-hand side is 1 ... to n is just literally 1. There's only one number that we're adding together. The right-hand side is n times n plus 1 divided by 2 is 1 times 1 plus 1 is 2 divided by 2, which is also 1. Therefore, the formula is true for n equals 1. Okay, so that was the base case. Now, assume that the formula is true for n numbers. For 1 plus ... plus n, we assume the statement for some n greater than or equal to 1. We know that it's true at least for 1. Now let's assume that there's some other number that it's true until. It's at least true for 1. So it must be true for some number of numbers, including starting at 1. Then we want to show 1 plus ... We want to prove this statement is true when you add the next number. When we add that next number, n plus 1, we want to see that this is true. That is, when you replace the number n with n plus 1 in the formula, then we get this formula. N plus 1 times n plus 2 divided by 2. So that's what we want to see. Again, we assumed that this part is true, so then we can replace it right there and say that how do we say this? So, because I made a complete mathematical sentence there, so let's start a new mathematical sentence here and say n plus 1. Well, then we can replace that first part with our inductive hypothesis and add the next term. N times n plus 1 divided by 2 plus n plus 1. Now we're just going to do a little bit of algebra to get to the answer. So I'm going to go ahead and do the right-hand side. I multiplied top and bottom by 2. And I distributed the n on the first term. Now we have n squared plus 3n plus 2, if we combine those two terms. And guess what? That does factor exactly how we want it to. N plus 1, n plus 2 divided by 2. Right? So, perfect. Therefore, the statement, when we assume that it's true for n, then the statement is also true for the next number. So P of n is true for all n greater than or equal to 1. And now we're done. There are fancy ways that you can state that you're done in math. You can use a nice little triangle, or not triangle, a nice little square. That is one way to say that you're done with your proof. And then another nice way to say that you're done with your proof is to say QED. And that says, like, it has been demonstrated. I forget the exact Latin, but it's Latin. So that's a fun little proof by induction. Let's do a couple more. There's some more interesting examples. And so we're going to work through this book. In general, I'm going to be solving exercises in lots of math books, okay? This channel is going to be about solving lots of problems. Solving every exercise, every math problem under the sun. It's going to be fun. So, hey, we got a like from somebody. That's nice. Somebody out there stopped by and gave it a like. Thank you. Yeah, so unlike my guitar channel, this is a brand new channel, and it has no viewers yet. So who knows if I'll get any viewers at all during this. We'll see. I've never tried starting a brand new channel from scratch, just live streaming. So this is going to be different. I don't know how or if this is going to work. Okay. So now, let's get a couple of exercises to practice. And this is from Andrew's number 3 textbook. Let's see. The first section is literally a section just about proof by induction. You know what? Why don't we give even more credit and say this is exercise 1-1, number 1. He uses a dash. He uses a dash for the sections, but I think that this looks a little bit nicer. We're just going to call this 1.1.1. The goal is we're going to now prove the sum of the squares. We want to see that this equals n times n plus 1 times 2n plus 1 divided by 6. Okay, so I did this in my other notebook somewhere else, but let's see if we can recreate it. I think that we should be able to. So, proof. So I'm going to be a little bit sloppier now. Base case, n equals 1. Then 1 squared plus ... n squared equals just 1 squared, and that's 1. And then n plus 1, 2n plus 1 over 6 equals 1 times 2 times 3 over 6, and then that equals 1. The base case holds, let's say, and then maybe all of this is demonstrating that the base case is true. And now for the inductive step, I'm going to assume that the sum of the first n integers matches this formula. So now I'm just going to replace those first terms, 2n plus 1 over 6 plus n plus 1 quantity squared. So I just went ahead and replaced the first n squares with the inductive hypothesis. So right here, inductive hypothesis. This is what we hypothesis. Whatever. So that's what we assume to be true for some n, for some number. And now, well, I think it's going to be the same type of trick that we did before. We're just going to distribute, collect the terms, and then factor, and then we should get the statement for n plus 1. So let's see what happens. This is going to be 2n squared plus, let's just do it. Let's do the extra step. So 2n squared, then we're going to have n, we're going to have 3n plus 1 over 6. And now over here, why don't we do this in 2 steps? This is going to be n squared plus 2n plus 1. And now we have 2n cubed plus 3n squared plus n all over 6 plus this term, which is going to be, now we're going to multiply top and bottom by 6, 12n plus 6 all over 6. Now we have, let's collect all the n cubed terms, 2n cubed. Now let's collect all the n squared terms. We have 9n squared. 9n squared. All the n terms is 13 of them. And then all of the constant terms, which is 6. all of that divided by 6. Cool. So now that we're here, we want to see that this factors in a special way. We kind of already know what we want to see. We want to show that it equals n plus 1 times n plus 2 times, so when we put an n plus 1 there, then 2 times n plus 1 is the same as 2n plus 3. We want to show that that top polynomial, when we combine those two terms together, that this is how this polynomial should factor. So that's nice because then I already have a hint as to how to factor this. So there's two directions here. We could take two strategies. One, we could use polynomial division to factor that polynomial. And I know what, like, some people know and remember how to do polynomial division, but not everybody does. It turns out that there is an algorithm for polynomial division, very similar to long division of numbers. That's one way, or we could show that the right-hand side equals this. So it's like we got the left-hand side ... to some to something. I'm going to call it x. If we can show that the right-hand side equals ... equals x as well, if we can show, then we got the left-hand side to this point and then meet in the middle from the right-hand side, then that's a perfectly valid way to show that the two are equal. So we could go either way. The first is maybe in some sense more elegant, but I think that it's easier to do it from the right-hand side. So I'm going to start out with solution 2. So since this is what we know we want to show, maybe I'll do it here then. No. Let's go here. Yeah. Right-hand side equals n plus 1, n plus 2, 2n plus 3 divided by 6 equals, let's go ahead and do this. We've got n squared plus 3n plus 2 times 2n plus 3 all over 6. I could be a little fancier and just skip the divided by 6 in every term, but let's just keep it as it is right now. Now we're going to have 2n cubed. We're going to have, and yeah, so I like to think when I'm factoring or like doing a distribution across two polynomials like this, I like to see it and think, okay, what are all the ways I can get an n squared term? What are all the ways I can get an n term? Or first, how can I get n cubed? Then it's going to be something times n squared plus something times n, and then some kind of constant. So I think that this is kind of the best way to think of doing this and to keep it organized in your head. So to get n cubed terms, the only way is multiplying this first term, n squared. This first term let me use a different color. This first term and this term, right? So that's the only way that we can get an n cubed term. Now, how can we get an n squared term? Well, we can do n squared and 3. So then we're going to have 3. Maybe I'll write that on the side. But then we can also do 3n times 2n. So that's 6. So then therefore there are 9n squared. The second term is 9n squared. Over time, you get better at just seeing that immediately and just kind of like doing it in your head. But I'm going to write it out for a couple of them, or at least maybe just that first one. Now, to get n, I see 9 when we distribute that and that. And then I see 4 when we multiply the 2 and the 2n. So 9 plus 4 is 13. And then to get a constant term, the only way is 2 and 3 multiply to 6. Now we have all of this divided by 6. So now we go back and see, do these match each other? Yes. 2n cubed plus 9n squared plus 13n plus 6 all divided by 6. So therefore, we showed that the left-hand side equals the right-hand side, and therefore, assuming that the statement, the proposition, was true, implies that the statement is true for the next number as well. And we're done. So that's the strategy. That is the method of mathematical induction. In another example, just for fun, let me show the other solution of polynomial division for those who don't know. We had 2n cubed plus 9n squared plus 13n plus 6. And we know that we wanted to factor out, we know that we want it to factor as n plus 1, n plus 2, 2n plus 3. So we want to factor out this this n plus 1 and find something that we can multiply it with so that they match. The long division approach here is you write the terms, you write the coefficients, 2, 9, 13, and 6. And then here, this is the root. So we want like a 0 of this polynomial is what we're working with. Like when you plug in -1 into this term, the polynomial factors as 0. So it's not +1, but -1 that we put there. We want, this should be a 0, like a number that you can plug into the polynomial, 0 of p of n. So, you start with a 0, with a root that you think should factor out, and you bring down this first term. This 2 gets written, you just pull it down, and then that -1 you multiply with 2 to be -2. And then you add these two numbers together. 9 minus 2 is 7. -1 times 7 is -7. 13 minus 7 is 6. -1 times 6 is -6. And then if everything went correctly, if this is a 0 of the polynomial, then this last term should be a 0. So it worked. It worked for us. In this case, we know that that original polynomial is n plus 1 times 2n squared plus 7n plus 6. These are the coefficients of the polynomial, of the other factor. Now, just like in long division, we can continue. And now we want to, what was it? -2 is going to be the next root. Oops. Let's do this one more time. Give ourselves a little bit more space. So we bring down that 2, multiply those. -4, 7 minus 4 is 3 times that. And then that works. So then, now we're basically done. Let's say that we've got n plus 1. Now here, this -2, that is the term n plus 2. And then here, this is 2n plus 3. 2n plus 3 is that last, those last coefficients, and we're done. And that is exactly the factoring that we wanted to see. So there's the second solution, was by polynomial division. Great, that was fun. Now let's do another one. Nobody's in the chat, and that makes sense. This is a brand new math stream, and nobody knows that I exist yet. Let's see. I proved all of these on my own. I think some of them were more interesting than others. Let's do exercise 1. This is going to be slightly different, but I think it's a pretty magical formula. This is one that I would like to show more people and just remind myself that it is a fact. Prove that. Often books will say prove or show that in this case, 1, 3, and then 2n minus 1. Let's move all this just a little bit. Let's move it maybe here. Cool. This is a pretty magical formula, I think. It is one that I want to show more kids when I'm tutoring them. Like, what is 1 plus 3? 4. What is 1 plus 3 plus 5? 9. 1 plus 3 plus 5 plus 7 is 16. So this is 2 squared. This is 3 squared. This is 4 squared. Like, that's a pretty incredible little fact. Like, that's something that's cool to show people, that you can show kids or anybody. And I think a lot of people don't know that one. Wrong tool. I wanted to erase all this, but I didn't. All right. So I'm going to say proof by induction. N equals 1 is clear as 1 equals 1 squared. Assume 1 plus 3 plus ... plus 2n minus 1 equals. So now we assume what the we assume the statement that we want to be true for all numbers, and then we want to show that if it is true, then it implies the next case is true. It's true for the next number as well. Like, i.e., the statement, the proposition n is true. Then what does this statement mean for the next number? Well, in this case, it's not going to be 2n. It's not going to just be 2n. Like, the statement is for the next number. So, I mean, we could write it like this. 2 times n plus 1, when we replace that n with an n plus 1, then we get 2n plus 1. Like that. Like, I don't know. I hope that that's clear. And let's keep that the prior term just for clarity. 2n minus 1. And then 2n plus 1. You can see that as like the next odd number is 2 more than the prior odd number. Like 2n minus 1 plus 2 is 2n plus 1. And then we can replace all of this with the inductive hypothesis. So we can assume that that all equals n squared, and then we add to the last term, 2n plus 1. And then, hey, guess what? That's exactly what we wanted to see. This factors really easily to n plus 1 squared. So, assuming the proposition for n implies that it's true for n plus 1, and we're done. Let's get a couple harder ones. This will be fun to match with my last video, which you can check out on my channel, because in the last video we defined the Fibonacci numbers, and I talked about how Fibonacci numbers, and I talked about how I show these to people, to kids or to anybody, as like a pretty good fun addition game. So the strategy is that you always add the last two numbers to get to the next one. So 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, on and on. Now, there are some really great formulas and facts that you can prove about the Fibonacci numbers. What's a good one? Some of these were a lot tougher for me than other ones. So I want to show two. One was really tough for me, and I want to work through that one together. But I think it's probably best to keep things simple with so this is exercise 117 from Andrews, is prove that f1 plus f2 plus ... fn equals fn plus 2 minus 1. So when you add the first n Fibonacci numbers, that it's going to be related to another Fibonacci number. So let's get some examples for motivation. Remember, f1 is 1, f2 is 1, f3 is 2, on and on. then when we add, when n is 1, then the sum f1 adding all the way up to fn, well, in this case, it's just f1, which is 1. When n is 2, then we have f1 plus f2, which is 1 plus 1, which equals 2. And now the statement claims that it should match fn plus 2 minus 1. So this is f3 minus 1. What is f3? It is 2. 2 minus 1, 2 minus 1 is 1. So those two match. Now this one is going to be f4 minus 1. F4 is 3. F5 is 5. Those are some good examples. So F4 is 3. F3 minus 1 is 2. And those numbers match. And then we have 5 minus 1, which is 4. So does this work? 1 plus 1 plus 2. Yep. So far these seem to be matching, which is neat. We could come up with more examples, but clearly it's going to be true. We're going to prove it here. So we're going to do this again by induction. When n equals 1, f1 is f1 adding all the way up to fn is just f1, which is 1. On the right hand side, fn plus n plus 2 minus 1 is f3 minus 1. Well, as we just showed, that is 2 minus 1, which is 1. So we're done with the base case. Assume that the proposition is true for n. And now we want to show that when we add the next Fibonacci number, that it matches, that we get, we're going to want to see n plus 3 minus 1 as the right hand side. So by assumption, we can replace this part of the sum with fn plus 2 minus 1. And then we have all of this plus fn plus 1. And then that is fn plus 1 plus fn plus 2 minus 1. And by definition of the Fibonacci numbers, this is fn plus 3 minus 1. Because we always have, because fn, I should use maybe a different letter here so that it's clear that I'm talking about a different thing. This is a general statement or a fact or definition of the Fibonacci numbers, that fk plus 2 equals fk plus fk plus 1. Or you could use minuses instead if you want. That's it. That we just showed that therefore assuming the proposition for n, we showed that it is also true for the next number as well. I hope that makes sense. Sometime in the future we'll have more people in chat. Maybe I should multi-stream this to my guitar channel for the time being so that some people will see it. If not, that's okay. Let's get a couple more examples. Maybe it's good. This forces me to actually just work through more problems. I had a tough time with exercise 15. I thought it was really lovely. So let's see if we can solve this one together. Or number 17. I don't know. I think all of these were excellent. I solved every problem in section 1. And I thought 15 was tough. So here's going to be a case where this math stream is not going to be me being perfect. I'm going to struggle sometimes. So that's the whole point of a practice channel, I think. Okay, so first, we need to define the Lucas numbers. This, I think, is really cool. I hadn't seen this before. They also have the same property that LK plus LK plus 1 equals LK plus 2. It's the same recurrence as the Fibonacci numbers. But they act a little bit different. They start with 1 and 3 instead of 1 and 1. So 1, 3, 4, 7, 11, 18, 1, 3, 4, 7, 11, 18, 29. That's probably enough for now. This will be useful to have as a table. Let's write out a few of the Fibonacci numbers and the Lucas numbers. 1, 1, 2, 3, 5, 8, 13, 21, on and on. And then the Lucas numbers are going to be 1, 3, and then 4. And yeah, so I'm looking at this from two different angles, and I'll show a couple of other facts about these. But 7 plus 4 is 11. 7 plus 11 is 18. 29. And then 47. Okay, so that should be enough. What we're going to see is what if we multiplied them together? What if we multiplied the two corresponding numbers? 1 times 1 is 1. 1 times 3 is 3. 2 times 4 is 8. 3 times 7 is 21. 5 times 11 is 55. 8 times 18 is 80 plus 64, which is 144. Okay, I think that that's enough examples for right now. I wonder if anybody out there sees any familiarity, any patterns about these numbers. Do these feel familiar? I think somebody who's really studying Fibonacci numbers might recognize all of those are Fibonacci numbers. So 13 plus 21 is 34. 21 plus 34 is 55. 34 plus 55 is 89. And then this one is... wait, did I get things off? Yeah, this one is 144. Okay. Yeah, for a second I thought I got my math wrong. All right. So 9, 10, 11, 12. So here, this 1 shows up right there. This 3 shows up right there. This 8 shows up there. This 21 shows up there. This 55 shows up there. And then this 144 shows up right there. Right? So it looks like we've got a great pattern. This one was just slightly off. So if we just modify this circle to be this one instead, because they are equal, 1 and 1 here, then every other number, like we're getting every other number to be, every other Fibonacci number is what we get when we multiply the Fibonacci number and the Lucas number. So I thought that was really cool. I hadn't seen that one before. And that's something that we could, that I think that you can show a kid and be like, oh, there's something in between, or there's some sort of connection between these Lucas numbers and these Fibonacci numbers. Like, isn't that neat? And all you have to do to introduce Lucas numbers is say, okay, well, it's just like Fibonacci, but we're going to start with 1 and 3 instead of 1 and 1. And then it's all the same sort of properties. So I think that this book actually defines Lucas numbers this way, and we will be using this, that the kth Lucas number is k minus 1th Fibonacci number plus the next Fibonacci number. So we can see that that is true as well. So we can see that this 3 is 1 plus 2. This maybe the 7 is 2 plus 5, on and on and on. Like, we can see all of these are 8 plus 21 is 29. So that is a perfectly valid way to prove, or sorry, to define a Lucas number. And then if you have this definition, you can prove that they have the same recurrence relation, or vice versa. You can start from one and then get to the other, or vice versa. Either way, you can prove one of these from the other, I think, by induction, again. So, but we're going to use both of those as a fact, and what we want to do is we want to prove that f of n times L of n equals f2n. This one was tougher for me. And I think I actually ended up using another result that I haven't proven here, and I don't think I have time to do. So I'm going to assume one fact, that if you add the odd Fibonacci numbers, 2n minus 1. If you add the first n Fibonacci numbers, that is also equal to f2n, I think. How does that work again? It's been a little... how does this work? Oh, yeah, it is this. Okay, that's what I thought. So this is another cool fact that maybe we could just focus on this one and show that this one is true by induction, and maybe leave the harder statement for the future. Yeah, you know what? Let's take that road. Let's prove this one first, and then next time I'm going to show this harder one. We're going to prove the sum of the first odd Fibonacci numbers equals the even Fibonacci numbers. And again, we're going to do this by induction. Maybe we'll get through it very quickly. When n equals 1, we have f1 is 1, and then f2n equals, well, f2, and we do also have f2 is 1 as well. So therefore the base case is handled. Now assume the hypothesis for some n greater than or equal to 1. Then f1, the sum of the first n odd Fibonacci numbers is going to be this, 2n minus 1. And then we want to show that when we add the next odd Fibonacci number, that the formula holds for the next odd number. Well, this first set of terms we assume is indeed f2n, and then, oh well, this was trivial. I forgot how easy this one was. Yeah, like by hypothesis, all of those equal f2n, and then you add that f2n with f2n plus 1, and now we have f2n plus 2, which is f2 times n plus 1. So now we're done. Okay, so that went faster than I remembered. Now we're going to get to the tough one. So let's see. You can tell that I have a little bit of anxiety about this, and it's because it took me like a few hours on the plane. I got so stuck trying to figure this out. So we'll see how this one goes. Maybe eventually I figured it out, so maybe it'll just come out easily here. Base case. F1 L1 equals 1 times 1 is 1. F2n equals F2 equals 1. Base case is handled. Base case is always generally super easy. It's super easy to show that you can knock over that first domino. That's not a problem. So that's not the part where I got stuck. Now, inductive step. Assume Fn times Ln equals F2n. Now we want to show which in math you often just say WTS as want to show. F of n plus 1 times L n plus 1 equals F, and it's the next even number. So you could put a parentheses, or you could just write F2n plus 2, right? Ooh, proof by induction. How's it going? Cheese, what's up? You're the first person today. So this is a brand new math channel. It is a practicing math channel. Welcome. And yeah. So I've been working through a few examples from this textbook, Number Theory, by Andrews. And yeah, so the idea of this stream is that I'm going to be doing simple things. Like I was showing, you've probably seen this before if you know proof by induction. Like a canonical great example that I show kids even is this proof of the first n odd number, or the first n numbers is n times n plus 1 divided by 2. And then this is a proof by insight. You know, Gauss was clever, but you can also prove that very easily by induction. So I defined and showed how to do a proof by induction. Then I worked through this exercise. The first squares, the first n squares is this formula. And then it's also a trivial proof by induction with polynomial factoring. This one was super easy as well. The first n odd numbers is n squared. This one was even easier, it's like super short. Now I'm doing a couple of Fibonacci examples. I did a Fibonacci, and now we're doing, this one is tougher for me. This one uses the Lucas numbers, which I didn't know about until I just started reading this book. The Lucas numbers are just like the Fibonacci numbers, but they start with 1 and 3 instead of 1 and 1. And then there's this beautiful theorem, or not theorem, or beautiful fact or something, that when you multiply the corresponding Fibonacci number and Lucas number, that you get even Fibonacci numbers. And this was a little tougher for me. So we want to show this relation between Fibonacci and Lucas. So let's start with Fibonacci n plus 1, Ln plus 1. Okay, how does this go? I'm a little stressed. All right, so this is Fn plus 1. Now here I'm going to use the recurrence relation, maybe that Lucas numbers also have like L1 plus L2 equals L3. It's the same, like add two numbers and get the next one. It's super cool, like super freaking cool if you ask me. I don't remember if this is how I did it, but it should work. Let's see. Fn plus 1 times Ln minus 1 plus Fn plus 1 Ln. Is this going to work? N plus 1. Maybe. So another fact about Lucas numbers, since you didn't see this a moment ago, is that a Lucas number is the prior Fibonacci added with the next Fibonacci. Like if you add every other Fibonacci number, you get the Lucas numbers, which is neat. Never seen Fibonacci with proof by induction. Yeah, well, there's an easier fact. You can rewind in the VOD or in the stream and you can see this fact I proved by induction. If you add the all the odd Fibonacci numbers, then you get the even Fibonacci numbers, which is super cool. Okay, so this, we might want to use this fact. So this would be, I can replace that Lucas number Ln minus 1 with Fn minus 2 plus Fn. And here, maybe I do the same thing. Fn plus 1 times Ln minus 1. Oh, wait, no. Fibonacci n minus 1 plus fn plus 1. So I replace that ln right there. Okay. Now, this is super... How the hell did I do this? Okay. I remember I got this thing down to... We can replace this fn plus 1 with like fn minus 1 plus fn. I'm going to get very stuck all the time in this math channel. I don't know if this is going to be the best approach on this. I don't think that this is the right approach. If we distribute out that first one, and then on the second one, fn minus 1 squared So it gets really dizzying, like how many of these terms, or like just writing like fn plus 1, fn minus 1 again and again. Like, I found this super hard to try to keep track of. But let's try to collect some terms. Did we get any repeated? So I just spotted those two were squares. I think that there's some that are, let's see, fn minus 1, fn... Okay. Here, that one and that one. So we do have 2 fn minus 1 fn. N minus 1, n minus 2, n minus 2n. Oh, perfect. Okay, wait. All right, so yeah, maybe this was the way that it worked. Okay, so we have those, and then we have some other terms. I'm going to continue writing out everything else, but notice that here, this factors as fn plus fn minus 1 quantity squared, right? Is that... What are we trying to show again? Fn plus 1... That's crazy. This is totally out of my league. Well, not really. I bet that you could learn this. What's your story? Do you study math? Have you learned? It sounds like you've learned induction. You recognized it immediately. Are you studying math? Have you done calculus or anything like that? Okay, so this I can see is fn plus 1 squared. for what it's worth. And then we get other terms. And then I think there was like another fact that's really handy to show this. Okay, you know what? I'm not ready for this right now. Next time I'm going to be able to reproduce this from memory and know exactly how it goes. Let me get my notebook. How did I solve this damn thing? This was like stumping me for a while in the airplane the other day. So how's it going? It's nice to meet you. This is a brand new channel. I hope hit the like and subscribe and all that. I've studied calculus a little bit up to differential equations. Heck yeah. Oh, you've never seen math like this. Nice, man. I think a lot of people haven't, but it's just gorgeous. Like, it's just fun. Like, in a sense, this is pure math, in a sense. Like, learning and really drilling and practicing proofs by induction. This is the first section of this number theory book. Number theory is about studying the whole numbers and patterns, relations, especially prime numbers, like understanding relations of prime numbers with other, I don't know. There's a lot of really great, cool stuff that you can see and show average lay persons out there. And most people don't study number theory unless you study mathematics formally. So let me just copy out this by rote to it took me like so many attempts to get this thing, so I'm not surprised that I don't remember. Where is it? Where is it? It's super messy because like I had so many failed attempts on this. Yeah, I had this claim that if I figured out the claim, then we were done. Whew. Okay, this isn't super different than what I was doing. Okay, typically with a proof by induction, don't you make an assumption though? Yes, so I did. The assumption is this is a statement that we want to prove. And so I've already done the base case. And so now we assume here, let me do these in red. Here's our inductive hypothesis. It's our assumption. And then I want to show, this is what I want to prove. So if I can massage this term to include these terms like Fn, Ln, then we can apply the assumption and then ultimately get it to the right-hand side. So I'm getting a little lost trying to find it, but we are looking for Fn, Ln. And you know what? That's a great point. Like, yeah, this is if we pause and think, okay, we want to apply this assumption that we had here. So why am I getting rid of the Lucas numbers too early? Like, I got rid of Lucas numbers right there, and I converted everything to Fibonacci numbers. So let's start over. Let's try it again. We want to show that Fn plus 1 times Ln plus 1 we want to show that this is equal to f2n plus 2. fn plus 1 ln plus 1 equals the Fibonacci number, that Fibonacci number, and I don't want to replace the Lucas number with the Fibonacci numbers. I want to replace it with the prior Lucas numbers. ln minus 1 plus ln. Now, let's keep things related to the Lucas numbers. Fn plus 1 ln. Now, we could replace that first Fibonacci number with because we have to use this recurrence. Fn plus 1 I can replace with Fn minus 1 and Fn multiplied by Lucas n minus 1. And then here, same thing, Fn minus 1 plus Fn times Ln. So what you're reminding me to do is that we can try to use the inductive hypothesis as early as possible. So just distributing through those terms. This was a tough problem. This is going to be the hardest one that we're doing in this stream today. And it's just so dizzying because there's like so many of these terms, F's and L's and N's and N plus 1's, N minus 1's. So I just distributed through, but now I'm going to use the inductive hypothesis twice. I see one there and I see one there. I'm also kind of cheating. I haven't talked about strong induction versus weak induction. But strong induction, you assume for all integers 1 ... You assume the hypothesis for all numbers, not just for a single one. So here I'm also going to assume the inductive hypothesis here, and you can prove strong induction from weak induction. It's just like it's considered a like a little bit of a stronger tool to use or something. So here we can replace this with the inductive hypothesis as f 2n minus 2, because here I have 2 times n minus 1, which is f2n minus 2. I'm going to reorder so that this other one shows up at the beginning of this term, of this line. Fn ln equals f2n, and now I'm just going to rewrite these. Okay, so I think that this is turning out a little bit different than how I solved it before, but it's potentially nicer. How do we want to do this? I guess I can do fn minus 2 plus fn minus 1. Yeah, this is a different proof than I had before, but I think that this is also going to work. So those first two terms are the same. Now I have fn minus 2 ln minus 1 plus fn minus 1 ln minus 1 plus fn minus 1 ln minus 2 plus fn minus 1 ln minus 1 So again, we can use the inductive hypothesis for that one. We keep getting this n minus 1 thing again and again. Yeah, so if I replace those with, again, the inductive hypothesis, we're going to get 3 f2n minus 2 plus f2n, and then I don't think that this is the right way to go. I think that this is going to be another one of those like long garden paths. I mean, by this process, we are reducing these numbers again and again, and we're going to be getting to a recurrence relation of some kind where at some point we can see a pattern and repeat and then say that that repeats indefinitely, and then I don't know. I literally don't know. What I ended up finding was that this problem was equivalent to fn squared plus fn plus 1 squared equals f2n plus 1. I found that the problem was equivalent to this, and that if you can prove this, then you prove the original. And next time, I think I'm going to come back and be a little bit more prepared, and I'll be able to solve this one. But in any case, nice to meet you, Cheese. I hope to see you again sometime. I'm going to try to stream almost every day, and sometimes I'm going to get totally stuck, like right now. So, yeah, we got there's a lot of really neat, little facts like these, and most of these, all of the other problems in this chapter were a lot easier. Like this one was exercise 119, f2 plus f4. If you add the first even Fibonacci numbers, that it's the next odd Fibonacci minus 1. Base case, when n equals 1, f2 equals 1, and f2n plus 1 is when n is 1, then this is f3, and F3 is 2, so 2 minus 1 is 1, so our base case is satisfied. Inductive step. So we know that the first n even Fibonacci numbers by hypothesis is f2n plus 1 minus 1. And then we add the next even Fibonacci number. Yeah, a lot of these are just like totally trivial. 2n plus 1 plus f2n plus 2 minus 1. This one, this is a super trivial example. F2n plus 3, because when you add two Fibonacci numbers adjacent, like 2n plus 1 and f2n plus 2, like those two add together to the next Fibonacci number, and we're done. This is 2 times n plus 1. Plus 1 minus 1. Is that? Yep. That's what we wanted to show. So the inductive step is complete, and then therefore the statement, if you assume it's true for n, then the statement is also true for the next number. And we're done. Cool. All right. Well, thanks so much. I don't know if anyone's still watching, but I appreciate you all for tuning in. I had fun here. I hope to see you all again sometime soon. Thanks for watching. I have one video that I've uploaded before, and go check it out. There's a lot of really cool stuff there. The other video that I have is more number theory for kids. Like, there's not any proofs, but I talk a little bit about partitions of a number. So like the number 4 can be partitioned as 4 or 3 and 1, 2 and 2, 2, 1, 1. Or 1, 1, 1, 1. I think that this is a really cool thing that a lot of people haven't seen. So these are all of the ways that you can partition the number 4. And you can define the definition of an odd partition and a distinct partition. An odd partition is going to be one where every number in the partition is an odd number. Like 3 and 1 are both odd, and 1, 1, 1, 1 is also odd. Those are the two odd partitions of 4. Distinct partitions are going to be ones where every number is unique. So like 3 and 1, those are unique numbers. They don't repeat anything. And the number 4, those are the two distinct partitions of 4. And it is a theorem that the number of odd partitions always equals the number of distinct. And that is amazing to me. Like, that is incredible. Like, that is such a cool, fascinating fact. You can run through this with 5 and you can see it. So that's one thing that I talked about in that other video. And then another neat one that I didn't get too deeply into, but I did talk a little bit about. Well, there was like Pascal's triangle. Talked about that for a bit. And these are like a few different facts, math facts that I like to show kids that I'm tutoring, like without proofs. Like Fibonacci numbers. But then another one that I love is Collat's conjecture. This one, it's a great opportunity to show a kid the idea of a function, show anybody a function. The first one is going to be dividing by 2, and then the second one is going to be tripling and adding 1. And a lot of people have never seen this, which is wonderful, I think. Collat's conjecture is the claim that if you keep repeating these two operations, like anytime that the number is even, you divide it by 2. Anytime that the number is odd, you'll triple it and add 1. That eventually if you keep repeating this pattern, the sequence will end at 1, at which point it just loops forever. So 5 triple plus 1 is 16, half of that is 8, half of that is 4, half of that is 2, half of that is 1. And then triple plus 1 is 4, and then you loop forever. 4, 2, 1, 4, 2, 1, 4, 2, 1. But then 7 is a little tougher. Triple plus 1 is 22, 11, 34, 17, 52. This is a great chance to show people some mental math tricks, like what is triple 10 and what is triple 7. Add those together. 26, 13, 40, and then we're almost done. 20, 10, 5, and guess what? We already did 5. So it's the same numbers as 5. 5, 16, 8, 4, 2, 1. Therefore, Collat's is true for 5. Collat's is also true for 7. We think, but we don't know why. This pattern was discovered about 100 years ago, that this sequence will always come down to 1, but we don't know why. And people have spent a lot of time trying to make progress on this really tough problem. Somebody named Erdos said that this problem is beyond the reach of modern mathematics, that math is not ready for such problems. All right, thanks for watching. Check out the other video if you want to see more about this stuff. And nice to meet you all. Thanks for tuning in. Bye. Bye.